All right, we're going to begin. We're going to continue our lesson, and we're going to talk about today, and then in the next lesson, two continuous random variables. One that we'll talk about today, and then one that we'll talk about in lesson 3. So a continuous random variable, this is, as the chart shows, is a random variable, has outcomes that occur either in a finite or infinite interval of real numbers. So the key here is that in this case, we're not talking about the discrete case where we can count the outcomes, or we can count the items that are outcomes that are in the sample space. These random variables occur on a continuum of real numbers from 0 to some interval, the ends of the interval, or perhaps this will continue out to infinity. And so these random variables are variables typically that are measurements, and things like time, things like length, things like weight, and height, and those types of things that can be measured, that the measurements only depend on the accuracy of the instrument that's measuring. And so these occur on an interval of real numbers, the real number line. So these are not going to be integers, they're going to be numbers that are of the form 1.2, 3, 4, 5, 6 decimal places that will continue on, continue and get as small as possible. All right. So let's look at one case of a continuous random variable, and this random variable we're going to see is very closely related to the Poisson random variable. And again, Poisson is a discrete random variable, but our exponential random variable is closely related to that, but it is a continuous random variable because this random variable talks about the time of the next customer arrival. You'll remember, for the case of the Poisson random variable, we're interested in the number of customers that arrive by time t. In this case, we're actually interested in the time that this next customer arrives, which is the random variable, right? And how that random variable, the realization, relates to this time window that we've specified of length t. Okay, so in this case, we have this realization. We've specified the time t, and we know that customer number 1, the first customer, arrives at this time, capital T. And you'll notice that capital T, which is a number, has a realization. Again, this is a variable that stands for a number, is greater than this point in time that we've specified, lowercase t. And if you think about this carefully, you can express this also being the same as how many, if we looked at this in terms of a Poisson random variable, how many customers will have arrived by time t. And hopefully you can see that this is the same as, this event is the same as saying that the number of customers that have arrived by time t is 0. So those are equivalent events. So let's continue and use this information to figure out and to calculate, if you're to compute what the cumulative distribution is for this exponential random variable. And then we'll look at a couple of examples. All right. So we already said that this is for a random variable defined as the time until the next customer arrives. If it's an exponential distribution, we notice again, just like before, that this is the time that that customer arrives is greater than our time window. And this is the same as saying that no customers have arrived in this interval of time. There you can see no customers have arrived. Therefore, this event is similar to this event. And so we can say that the probabilities are equal. So that the probability that the time of the first arrival is greater than t is the same as the probability that the number of customers that arrive by time t is at 0. And now using our Poisson distribution, we know lambda t to the 0 raised to the 0 power times e to the minus lambda t over 0 factorial. If we remember from last time, of course, this is 1. By definition, this term is 1, and so that just leaves us with e to the negative lambda t. So now what we can say is the following, is that the probability that the time that the next customer arrives at a location is greater than t, that probability is e to the negative lambda t. All right, so that's our first step. Our next step in that process is we actually want to know the cumulative distribution. And this is called the CDF, or the cumulative distribution function, where we can calculate the probability that the time that the next customer arrives is less than or equal to t. So if you were opening a store, you'd want to know what's the chance that I'll have one customer before in the next 30 minutes or the next 15 minutes. And in order to do that, this is the complement of what we've just calculated. And by probability definitions, the probability that t is less than or equal to this time that the customer arrives is 1 minus the probability that it's greater than that time. And we already know that from our previous work that this value, which is the same as here, is this value. And so what we do is we substitute this into this equation for this term, and we come out to 1 minus e to the minus lambda t, which is the probability that the customer arrives before the next customer arrives before time t. Okay, and so therefore that cumulative distribution function is that value. And again, much like with the previous, there's only 2 terms here where we have our Greek letter, our parameter lambda, and again, this is the customer arrival rate. And I want to emphasize this. This is an arrival rate. And again, some of you unfortunately will make this error, but it's the arrival rate. And again, our value of e, it's that same constant, it's transcendental number that we saw for the Poisson distribution. All right. So let's see how we're going to use this to solve problems and to answer questions. And as we talked about before, this is the process. We want to make sure that we identify the probability distribution. We want to be sure to define the random variable, then define the parameters, and then translate that problem into a probability statement, and then translate that probability statement into the PDF or CDF. And in this case, we're going to be looking at the CDF. And then we're going to substitute the values, do the calculation, and then answer the question. So that's the process that we're going to go through. And let's see this in an example. And so here's an example. The time between calls to a plumbing supply business is exponentially distributed with a mean time between calls of 15 minutes. And so the first question is, what is the probability that the call does not arrive until after the next 30 minutes? So probably this could be a scenario where you are working by yourself in a shop, and you want to take a lunch break. And so you want to know what's the chance that you're in a call center, what's the chance that you can go take your lunch break and that you don't have a call in that 30-minute window. Given that the average time, and again, I want to make a point here, this term mean, whenever it's used, it's the same, it's exactly the same as saying average. Same as saying average. And so, so I can say with an average time between calls of 15 minutes. So that means, again, if we were to look at a timeline, then on average, if you took the time between calls, and this is time 1, and that we get a call here, we get another call here, and we measure the time between calls here, we get another call here. This is call number 3, and then we get another call way out here. And this was time 1, this was time 2, this was time 3, this was time 4. If we averaged up all of those, on average, the time would be 15 minutes. But that doesn't tell you about the rate, and we're interested in the rate. All right, so let's use our, which we'll do that rate in a minute, but let's look at, first of all, what we want to do. Let's let C be the time of the next call. That's our random variable. Then what we want to do is we want to find, we know that it's C is distributed exponentially. That's a EXP. And it has the parameter lambda. All right. And then what we want to do is we want to determine what is the probability C is greater than 30 minutes. And I'm not 30 minutes, I'm just going to write M, 30 minutes. Okay. So then what we know is the next thing that we need to determine is what's T, and in this case, T is our time window that we need to take our lunch break on is 30 minutes, and our parameter lambda is the call rate, and in this case, we get the rate of calls is that we get 1 call per 15 minutes. one call per 15 minutes. And so therefore, lambda times t, one call per, or if you will, then you can also express that as 1/15 calls per minute. And lambda t is now 30, and I'm going to write it this way, times 1/15, which is 30 over 15. And we're probably already there. This is lambda times t is 2. All right, and so now that we know this, what we want to do is we know that this is this is 1 minus the probability that that call comes in less than or equal to 30 minutes. Okay, and this then, by using our, substituting our definition, this is 1 minus e to the minus lambda t. And when we do the arithmetic, this is 1 minus 1 plus e to the minus lambda t. And you'll notice that 1 minus 1 is 0. And so this just leaves, so this is 0, and that those terms cancel. And so that just leaves us e to the minus lambda t, and now I'm going to substitute in here. So this is e to the minus 2. And when you do this calculation on your calculator, it turns out to be 0.1353. Okay. So that's how we're going to how this problem works out. Okay, next, let's go to another example. What's the probability that the first call arrives within 10 minutes after opening? So now we have the same random variable, but what's happening here? Here's our timeline. This is time 0 when we open, and we've got here's 10 minutes. 10 minutes. We want to know the probability that the call arrives within 10 minutes. We already know from our previous work that C is our random variable. We know that lambda hasn't changed. It's one call per 15 minutes. We know in this case what's T, because we want to determine the probability that that first call, the time that that call arrives, is less than or equal to 10 minutes. And in this case, T is 10. And if you'll notice here, I'm going to do this a little bit quickly. Lambda T is 10 over 15, which is 2/3, 0.6 repeating. Okay. And so now we know by net definition, this is the CDF. We can use the CDF directly, which is going to be 1 minus e to the minus lambda t. And we know that lambda t is 0.6 repeating, e to the minus 0.666 repeating. And when we do the arithmetic, this is 1 minus, this term then becomes 0.5132. And so the answer for this is 0.4868. So there's just under a 50% chance, 49% chance that that call will arrive within 10 minutes. Okay. One of the things I want you to notice is the following. Let me see if I can get this done here. Let's suppose this were in hours. Then the rate, if we wanted to use hours, the rate is if you get one call every 15 minutes, then your phone arrival rate per an hour is, you would get on average 4 calls per hour. And in this case, since we're on hours, t is not 10 minutes, t is 1/6. 10 minutes is 1/6 of an hour, or 10 divided by 60. All right, and so we would still have lambda t equals 4 times 1/6, which is still 2/3 or 0.66 repeating, just as before. So these are the same values with lambda t expressed in terms of hours, or lambda t, or excuse me, lambda and t expressed in terms of hours or in minutes. The point being that in either case, whichever case you use, these terms for the rate and for the time window must be expressed in the same units of time, and that leads to that these two terms are the same. So our next slide is a cleaned up version of what I just took you through. So be sure to study this and take a look at this, and let me know if you have any questions. All right, thank you. Hope this makes some sense to you. Take care. Bye.